Welcome to the last session of PriSC and the last session of Popple. So I have been asked to try and stick to the schedule because it's sort of the last session of Popple. So I will quickly try to give the floor to Ethan. Ethan will tell us about secure compilation in a context we haven't heard yet today, which is cryptography.
Great. Thank you, Dominique. So yes, as he said, this talk is really about connecting two domains. And given where we are right now, it should be pretty unsurprising that one of those domains is programming languages. And given that Marco is one of the chairs of this workshop, it should be also pretty unsurprising that specifically I'm going to be talking about robust compilation on the programming languages side. And the second domain, as Dominique mentioned, is cryptography. And in particular, I'm going to talk about universally composable security, or UC security. And so we want to connect robust compilation and UC security. Now, I don't expect everyone in here to know what UC security even is. So as a quick primer, this was originally introduced by Ron Künnemann a little over 20 years ago. And it's a framework for defining and proving the correctness and security of cryptographic protocols in a way that ensures that they compose really nicely. So at a very high level, you take an actual protocol, which we're going to call Pi, and it has a bunch of different machines, and they're all talking to each other. And we're going to define the correctness and the security of Pi with a so-called ideal protocol. And an ideal protocol, instead of having all the machines talking directly to each other, it has all the machines talking to a sort of magical trusted intermediary that's known as the ideal functionality. And the ideal functionality defines what it means for the protocol to be correct and secure. And at a high level, the security proof would work as follows. We would say that for every attacker, right, maybe we replace one of the machines has been compromised by an attacker. And so for every possible attacker who can compromise that machine, we need to be able to find some simulator such that both of the sides of this diagram kind of look the same as each other. And they need to sort of behave the same way. And that notion of behavior is that we're going to take some environment and we're going to put the same environment on both sides. And we're going to say from the environment's perspective, this has to look the same. And we quantify over all possible environments. So that's what universal composability says. It says if no environment can tell the difference between these, then the protocol is correct and secure. Well, as sort of a recap, what does robust compilation look like? Well, there's a lot of different kinds of robust compilation. We've heard about multiple different kinds already today. And specifically, I'm concerned with robust hyperproperty preserving compilation, or RHC. This is from the Journey Beyond Full Abstraction work from CSF 2019. And in this context, we have a compiler, which in this case we'll say takes these blue square programs to these orange circular programs. And we say, well, for any source language program and any target language context, we have to be able to find some source language context such that the behaviors of these are exactly the same as each other. But we can, that's sort of the original formulation. We can take that formulation and we can look at it slightly differently. We can, in particular, we can split the context into two pieces, right? We can sort of think of the context as an adversary, and then there's some environment, and all the environment is doing is it's supplying inputs to the whole system, and then it's just going to watch an external view of what's going on. The adversary is going to do all of the actual work that the context was doing. And we say, well, we can sort of do the same thing on the other side, right? We can say, well, there exists a simulator that does the same thing. In the context, it's just providing external inputs and it's when watching what's happening, nothing else. So it's going to be the same environment on both sides. And so instead of behaving the same, we can say, well, these kind of look the same to that environment. Boy, this looks familiar. This picture's kind of the same picture as the UC picture we had up earlier, right? I can just put these next to each other. And these have exactly the same structure. And so we'd like to relate these, but if we want to relate them in a really technical sense, we need to have definitions for things. And more formal definitions than just sort of this wishy-washy hand-wavy stuff I've been saying. And the first one I want to talk about is this notion of looking the same. I have not told you what that means. And there's a lot of different ways to define looking the same. The simplest one is just equality. You just say these two things have to be exactly equal. And if we do that, we actually get very well understood notions on both sides. We get something that's called perfect UC security. These behave exactly the same. And we get standard robust hyperproperty preservation on the robust compilation side. And thanks to some work by Marco, as well as my co-author on this, Robert Künnemann and Riyad Wabi, we actually know that these do fundamentally deeply represent the same thing. That's not new to me or to the paper I'm talking about here. But unfortunately, on the UC side, that equality symbol is kind of a problem. Perfect UC security isn't very useful in many contexts because real cryptography isn't perfectly secure. Real cryptography is only secure against computationally bounded adversaries. It makes hardness assumptions on the difficulty of computing problems that are often trivially decidable. They just require perhaps exponential time. So let's fix this. And to fix this, let's look at what people actually use. And on the UC side, we have a well-understood notion of what people actually use, which is computational UC. And this is to handle the fact that, as I said, cryptography needs computational bounds. So we can take the same picture we had before. We can just start kind of tossing computational bounds on it, right? We can say, well, the attacker has to run in time polynomial in the length of the input. And the simulator also has to run in time polynomial in the length of the input. We're not going to care about attackers that take longer than that, and we're going to require that our simulators be that fast. We can say, well, the environment's only allowed to use polynomially much computation to try to tell these things apart. And the last thing we can do is we can put a weaker notion of looking the same onto this that's referred to as computational indistinguishability. And this just says that they don't have to be exactly the same, but to the perspective of this computationally bounded environment, the difference between them, its ability to tell which side it's in, has to shrink really, really fast as the length of the input grows. Really fast here usually means exponentially fast. So this is what actual computational UC looks like. This is what people in the cryptography world use when they're talking about UC security. And so if we want a notion of robust compilation that corresponds to this in any meaningful way, we need a notion of computationally robust compilation. We need to sort of get these computational bounds into the robust compilation world. So to do that, where's the problem, right? Well, robust compilation talks about all contexts and demands that the behavior be exactly the same. So to fix this, we're going to talk about computationally robust compilation. We're going to restrict the context. We're going to restrict the attacker and the simulator to be these polynomial time contexts. And now we have the same thing we had on the UC side, right? We only care about polynomial attackers, and we require the simulator to be polynomial time. And we can also replace this equality with indistinguishable behavior, which sort of absorbs the polytime environment into it. Now, these are really simple changes I've made here, but I want to point out that they're also a fundamental extension to the robust compilation framework. The robust compilation framework doesn't really have a way to talk about this, and so we need to add one in to be able to make these sort of conceptually simple changes. But when we make them, we end up with a notion of computationally robust hyperproperty preservation. And I want to look at this just a little bit more technically, right? Robust RHC, the standard one, the one from the Journey Beyond Full Abstraction paper from a few years ago, it says that for all programs and all attackers, there exists a simulator such that these look the same, right? But we really fundamentally cannot put any restrictions into these holes. And to get computationally robust compilation, we have to put restrictions into those holes. So we're extending the framework to do this. And we make this change, and we made it to follow the process of UC security. And so the last step is to make sure that these changes actually did what we wanted, right? And indeed, we're able to prove that it does do what we want. We can get this theorem that says that computationally robust hyperproperty preservation corresponds precisely to computational UC emulation between the source and target programs for all possible programs. So part of me wanted to just end the talk here and say, hey, look, we did it, right? But I was told I was supposed to talk for about 17 minutes, and I don't think this has been anywhere close to 17 minutes. So there's a few other aspects of this that I want to get into. And the first one is about classifying preservation of hyperproperties. So I described robust hyperproperty preservation by saying the source and target programs had to have the same behavior. But there's another way to look at this that is, again, not new to us, right? This comes from the Journey Beyond Full Abstraction paper, to say that robust hyperproperty preservation is, as the name would suggest, preservation of all hyperproperties. What that means is that for any hyperproperty H, if the source program always, we have a source and target program, right? If the source program always has behavior in H, then the target program is also always going to have behavior in H. But what about the computationally bounded case? What does that look like? Well, at its core, computationally robust hyperproperty preservation is actually preserving computational emulation. So that means that for any functionality, right, this is sort of one of those ideal functionalities, for any functionality, if the source program emulates that functionality, then the target program also emulates that, computationally emulates that functionality. Now, this might sound like a statement of, this might not sound like a statement about preserving hyperproperties, but it kind of is. Because emulating F here means that all of your behavior looks indistinguishable from the behavior of F. So we can just take the set of behaviors that look indistinguishable from the behavior of F, that's a hyperproperty, and say that you're in that. Your behavior is in there somewhere, and that's a hyperproperty that we call CH. For, I think it's the computational emulation hyperproperty. And the computational here, though, this is not actually exactly about the hyperproperty specifically. We also need to restrict the class of contexts we look at the same way we did before. So this is actually going to put the same restriction. We're going to need the same extension to the framework that we had before to even state this computational requirement. But indeed, once we put all of that together, we get exactly what we were looking for, right? This CRHC thing I was talking about earlier is exactly the same as a polytime preservation of emulating every possible functionality. There's one last thing I want to say, which is in a somewhat different direction, and it's about generalizing this. So I never really defined polytime, and I barely defined computational indistinguishability for you. And you might have assumed that's because these have totally standard definitions and because I was trying to make things simple so that the talk would be understandable. And you're not wrong. But that's not the only reason I didn't define them. I actually didn't define them because fundamentally, for the math to work out here, the definitions don't matter. In fact, in the paper, we prove something considerably more general. And the first thing that we can do is we can replace these polynomial predicates with just arbitrary, uninterpreted predicates on programs. And we can do the same thing for indistinguishability. We can replace it with a totally arbitrary equivalence relation. And now we have a way more general property that we refer to as predicate-robust hyperproperty preserving compilation. And the neat thing is, this generalization buys us quite a lot. It really works, right? And so what do I mean by it really works? Well, it represents a bunch of different stuff all at the same time. The simplest version is we can give a trivial predicate true. So this allows any program in any context to be considered. And we can demand full, complete behavioral equality. This devolves into exactly robust hyperproperty preservation. And we already know that corresponds to perfect UC security. We could also go in the other direction. We could demand that everything be polynomial time and only care about computational indistinguishability. And this pretty immediately devolves into computationally robust hyperproperty preservation, which we proved in this work is equivalent to computational UC security. That's cool. We've managed to catch both of these, but we do not have to stop there. We could, say, allow for arbitrary programs, but only demand indistinguishability. This doesn't correspond to any sort of robust compilation property I've already told you about, but it does correspond to a notion of UC that exists and that we understand, which is statistical UC security. This requires that the behaviors be statistically close to each other, but they don't have to be exactly identical. We could go even farther if we wanted to. There's a bit of a rabbit hole here, right? For instance, we could use sort of some weird equivalence that's very weird in this context, but not in other contexts. We could require the equality of behaviors when restricting to things that a certain security level. So this could essentially tracks whether or not secrets are leaking. It corresponds to an information flow style non-interference definition. I have no idea what kind of UC security this corresponds to. I would be shocked if it corresponded to anything that's already in the literature. But the thing that's really neat here is that this work gives us the language we need to start talking about that and to start investigating it and to really make these connections more broad and more deep all at the same time. So where are we, right? What have we done? Well, I told you about a generalization of the robust compilation framework to get this notion of predicate robustness. And I showed you how we can use this to define computationally robust hyperproperty preservation, and that corresponds precisely to computational UC security. And that this polynomially preserves this class of hyperproperties. All of the proofs are verified in Isabelle Hall. We have machine checks proofs for everything. There's also in the paper, we use this to support a UC proof of a model of the Wireguard protocol using CryptoVerif. And the full paper for this should be on my website as of a couple hours ago. I should probably check to make sure it deployed properly. And will be appearing at CSF this upcoming summer. And with that, I would be happy to take questions.
Questions?
Hi, cool stuff. You showed that we can go from the one direction to the other, and that we can generalize this. But hyperproperty preservation is just one of the many secure compilation criteria we already knew of. Do you know whether this also works if we go for something like relational hyperproperties or just anything else that we already know about?
The short answer is the generalization of the robust compilation framework should translate with no problem to those. Those, so far as I'm aware, do not correspond to a meaningful notion of security in the cryptography world that people use. This was actually a sort of an open question for quite a long time, is what is UC security, and all of these other sort of cryptographic definitions, what do they correspond to in the PL world? And we think the answer is, robust trace property preservation and robust relational hyperproperty preservation don't really seem to correspond to something that people use. But Marco's going to disagree with me. No. Yes, okay.
There's something worth adding here. It's that depending on the trace model, and the UC trace model is very funky. There's a lot of collapses. If you know the diagram from the journey beyond full abstraction, there's many points, there are many elements in that diagram. Now, it turns out if you start adding language features or constraints on the trace model, some of those things collapse. I don't remember these collapses by heart, though, with the UC trace model, but if I remember correctly, I think all the relational stuff gets squished down to RHC. But I don't remember. There's a long time ago.
Now that you mention this, I also remember there are different UC models, and in some of them, there's a quantifier ordering that I sort of had implicitly on my slides that is the classic UC quantifier ordering. And in some UC models, you can actually reorder some of those quantifiers and get things that look like they should mean very different things, but actually collapse. And it really depends on the model. There's a bunch of models floating around out there. Yeah.
We have time for one more, maybe two questions if it's brief.
So yeah, I wonder about this last point. Like, how did what you presented help you with this proof?
Yeah, that's a great question. Unfortunately, the right person to answer that question is Robert, who's not here today. But essentially, what it lets us do. So CryptoVerif is a tool that's designed for proving computational indistinguishability, and what this does is it gives us sort of a deeper understanding on the PL side of how computational indistinguishability relates to UC security, right? So using a tool that is sort of more of a formal verification tool designed for computational indistinguishability, making sure that that actually corresponds to a full UC proof is something that we didn't have the framework to really properly talk about what was definitely necessary before.
Interesting.
Yeah. Okay, thanks.
So maybe while the next speaker sets up, I can ask a final question.
Yes,
so
please.
is there some way to instantiate your framework to get some kind of quantum resistant security? Or?
Ooh, that is a great question. I have not thought of that. My guess is that most of the computational model and the predicates are left fairly abstract. So my guess is that if we instantiated the computational model with a quantum computational model and the predicates with an appropriate notion of fast for the computational setting, it would be able to talk about that. But that's not something we've directly investigated, and I don't know what the ramifications would be.
Okay, so the next speaker